Hello everyone, this video covers sections 3.9 and 3.11 from the textbook. Section 3.9 is called moments and moment generating functions. Before we go there, let's just refresh your memory in what we've done so far. So far we talk about random variables. We specifically talk about the binomial, the geometric, hypergeometric, and Poisson. Hypergeometric and the Poisson distribution. Okay. And remember, each random variable has a expected value and it has a variance. Okay, any random variable, not just these ones. And remember the definition of expected value was equals to the sum of x times p of x, or sorry, it should be y p of y. So y times p of y. And then the variance, we have two formulas, but you could say the expected value of y squared minus the expected value of y squared, which also, remember, for notational purposes, this one is usually called just mu, and this sigma squared. So for the binomial, the mean was just n times p. The variance was n times p times 1 minus p, or npq. This one was 1 over p. And this one, the variance was 1 minus p over q squared. And then the hypogeometric has a pretty long one, which I'll just skip for now. And the Poisson is the easy one, which is just lambda and lambda. Remember, this was the only distribution that it has the mean and the variance are the same. So the hypergeometric is n times r over capital N, and this one was n times r over capital N and minus r over n times n minus n, or n minus 1. All right, so again, this is what we've done so far. So we're going to use some of this information right now, so that's why I review it. So here is the first definition. The kth moment, okay, all of this is going to be related to expected values of a random variable y taken about the origin, meaning 0, is just defined to be the expected value of y to the k, and the book uses this notation mu k prime to denote the moment. So obviously, if you look to this, if k is 1, right? So if k is equals to 1, we have e to the y to the first power, which we define that to be mu. So the first moment is just the mean, or you can say that this is mu 1 prime. Okay? Now if k is equals to 2, it will be e to the expected value of e to the y squared, and this will be mu 2 prime. So therefore, all of these are the first moments for these random variables. Now let's go to the next definition. This is a little more general. The k moment of a random variable taken about its mean. So now we are going through the mean instead of the origin, or it's also called the k central moment of y, is defined by this. And technically, we did this definition before. Remember that this one you can also rewrite it as the expected value of y minus mu squared. So in essence, if k is equals to 2, then this is the actual definition that we have for the variance for any random variable. Okay? So the second moment of about the mean is another name just for the variance. Okay? or using the notation we have right now, you can say that is equals to mu 2. Now the notation is not the best, so make sure you keep track of that. So here, remember the 2 here means the second moment above the mean. Well, here mu 2 prime is the second moment above the origin, and this is the one that we'll be using more often. All right, so now let's go to the last definition of this section, which is the main thing. The moment generating function m of t, okay? So this function, like the name suggests, is going to be used to generate moments, where these are the moments, okay? Is defined to be this. So the moment generating function for a random variable y is defined to be this. And as long as the expected value is finite, then this exists. Right, so here, notice the definition actually implies this. M of t equals to the expected value of e to the ty, where remember y is a random variable, so y is a random variable. I'm going to use this over and over. I mentioned this before for random variable. By definition, remember this is equals to the sum over all the possible values of y of e to the ty times the density function. So that's the definition we're going to be using. Okay. Now, why is this called a moment generating function? Well, if you recall from calculus 2, okay, which I know was maybe a while ago for some of you. Remember, e to the x is equals to the sum of x to the n over n factorial from n equals to 0 to infinity, or 1 plus x squared over 2 factorial and so forth. Therefore, if we combine these two definitions, we will get the following. We will get that the moment generating function, it will be equals to the sum from y, and then notice that e to the ty is equals to this. So we use that definition, that will be equals to 1 plus ty plus ty squared over 2 factorial plus ty cube over 3 factorial and so forth, and all of this multiplied times p of y. Okay, the only difference here is the our x value that we're using. Our x is equals to ty. Okay, now if you expand this, then this is going to be equals to the sum of y over py plus, you can take the t out since we are summing with respect to y. It will be y py and then t squared over 2 factorial, the sum of y squared py and so forth. So now notice that this is equals to 1 because that's the sum of all the probabilities. This one is technically the expected value, so that will be t times mu 1 prime, and then this will be t squared over 2 factorial, and now this is the second moment, which by definition is mu 2 prime, and by definition I mean this, the first definition we were using. So this is the first moment, this is the second moment, and so forth. Now what we're going to do next is we're going to use this actual function to generate these moments, and the idea is actually pretty simple. Notice the following. Here, if you plug in 0, obviously everything here will die and you will end up with 1 only. But if you take the derivative with respect to t, then this obviously will be 0. You will only have here the first moment, and here you'll have 2t times that. But again, if you plug in the value for 0, all of this will disappear, and the only thing you will have left will be this, which is the first moment. So pretty much to find the moments, you're going to take the moment generating function, you're going to take the derivative, and when you do the derivative, you're going to set at t equals to 0, and that will give you the moment that you want. All right, so that brings us to officially the theorem, but this is precisely what I just stated right now. If mt exists, if the moment generating function exists, then for any positive integer k, this will give you the moment, which means you take the derivative and then you evaluate it at t equals to 0, and that will give you the k moment that you want. Now recall, we just did this right now, but on the last page, recall that m of t was equals to 1 plus t times mu 1 prime plus t squared over 2 factorial, then mu 2 prime, and so forth, tq over 3 prime, mu 3, sorry, over 3 factorial, then times mu 3 prime. Okay, so therefore if we do the first derivative of this, notice this will be 0 plus mu 1 prime plus 2t over 2 factorial mu 2 prime 3t squared over 3 factorial, and so forth. The point is that if we plug in a mu prime of 0, you will only end up with mu 1, and the rest will be 0. So that will give you the first moment. If you take the second derivative, so this implies that we do mu 2 second derivative, and then with respect to 0, this will give you the expected value of y squared, or what we call mu 2 prime. Notice that here 2 over 2 is 1, so you only have t, so you take another derivative, it will just give you this. Okay, so you should check it, convince yourselves, but that's what it is. So now we're going to use this to generate expected values and variances, which some of them you already have it, so this is a way to verify that those are the actual expected value and means and variances and standard deviations. So let's start with a binomial distribution. So here let's say that y is binomial and has a value for n and p. So we already know that the expected value for a binomial is equals to n times p, and we know that the variance is equals to np times 1 minus p. Okay, so you should all memorize this. So now we will see we get exactly this using moment generating functions. Okay, so by definition, the moment generating function for this variable is the expected value of e to the t y, where y has to have this distribution. Okay? So then, like I mentioned in the last page, the binomial is defined only from 0 to n. So there will be e to the ty times p of y, which is equals to the sum from y equals to 0 to n of e to the ty times p of y, which is n choose y, then p to the y times 1 minus p to the n minus y. Okay, and then notice that you can combine these two, so then this will be equals to the sum from y equals to 0 to n of n choose y, and then this will be e to the t times p to the y if you combine these two, and then with this, and then times 1 minus p to the n minus y, or the book just calls this q. So q and 1 minus p, remember, is the same thing. Now, you remember also from pre-calculus, okay, so recall way back from pre-calculus, you wanted to expand this. There is a reason why it was called a binomial expansion. That was equals to the sum from y equals to 0 to n, or n choose y, and then it will be a to the y, b to the n minus y. Okay? So therefore, using that formula, clearly this will be just e to the tp plus q to the n power. So that's the moment generating function. So now that we have the moment generating function, we can use it to find the mean and expected value. Remember, the mean has to be np, so let's see if that's the case. So if we do the derivative with respect to t of m of t, in our case it will be n times e to the tp plus q to the n minus 1 times the derivative inside, which is et times p. Then we evaluate the derivative, remember at 0, so then it will be n times e to the 0 times p plus q to the n minus 1, and then this will be e to the 0 times p. Notice that for the binomial, p plus q has to be always 1, so this will be n times 1 to the n minus 1 times p, but 1 to any power is just 1, so this is n times p, which is exactly the mu that we had before, so that's perfectly fine. So this gives you the first moment. Remember, this is exactly the same thing as this, so don't forget the notation. You want to find the second moment, which means you want to find the expected value of y squared. Then you just have to use the product rule and the chain rule. This will be the derivative with respect to time of the first derivative. The first derivative was equals to this n e to the tp plus q, and since you have a product, you have to use the product rule and the chain rule. So just give it a try. That should give you the answer. All right, now let's try the exact same thing for the geometric distribution. For the geometric, and I believe this is one of the homework problems, the moment generating function is equals to p e to the t over 1 minus q e to the t. So that's the moment generating function. You should try to get this using the geometric distribution. I do believe it's one of the homework questions. Okay? So therefore, if you want the expected value of y, which remember this is the first moment, or mu, and you already know the answer should be 1 over p, just for the record, then this is going to be the derivative with respect to t of the first, of the moment generating function, which is this. Okay. Now, so this is a quotient, you have to use the quotient rule. So the derivative is equal to the derivative of the top times the bottom minus the derivative of the bottom times the top. Okay, or f prime g minus g prime f over gq, depends how you learn this, and then over 1 minus q e to the t squared. So that's the first derivative. So therefore, the first derivative, if you evaluate it at 0, notice here that on the top, this will cancel with this one. So you will have left p e to the t on the top, and the bottom is 1 minus q e to the t squared. So if you plug in 0, it will be p over 1 minus q squared. But remember that 1 minus q is the same thing as p, so this is p squared, so it will be 1 over p. Which is exactly the expected value. Okay. All right, so let's do a couple more of examples. So suppose that y is a random variable that has a moment generating function m of t. Now just to refresh the memory, y should be m of 0. Remember that m of 0 has to equals to 1. We checked that already. Just go back to the previous pages. For part B, let's say that we have a new random variable w, which is 3 times the random variable that we already have, which is y. And you want to know now what's the moment generating function for w, okay? Given that you know the moment generating function for this one. Remember, so m of t here, well, by definition is equal to the expected value of e to the ty. Okay? So in our case, since w is equal to 3y, this should be the expected value of e to the t w, which has to be e to the t times 3y, which is the same thing as the expected value of e to the y, you can say times 3t. So therefore, this is the same thing as the moment generating function of y, but evaluated at 3t instead of just t. Now for part C, let's define a new variable x, which has to be related to y. And again, the question, what is the moment generating function for this one? So in this case, we need m of x, and by definition, this is the expected value of e to the t, and this will be y minus 2. So notice that you can take out the minus 2t out, and it will be the expected value of e to the t y, which by definition is just the moment generating function of y evaluated as t. Alright, let's try another very similar example, just in case that one didn't make a lot of sense. This is the chance to redeem your sins. So you still have a random variable y that has a moment generating function m of t, which you can just call it m of y of t for now. And we're going to define a new variable. So let's say now the w is equals to a y plus b. We did this problem already with a completely different method. So just to verify we get the same thing, where a and b are constants, okay? So what will be the moment generating function of w? So again, by definition, it should be e to the t w, which will be e to the t times a y plus b, which you can see it will be e to the t b. You can take that out because b is a constant, and then it will be the expected value of e to the t a y, but by definition of moment generating function of m of y, this just will be m of y evaluated at at. So therefore, if we want the expected value of w, that means we need to find the first derivative and evaluate it at 0. This is what we want, so that will give you this. So what is the first derivative of m? First, since you're taking that into respect to t, and you have a product here where this depends on t and this depends on t, you have to use the product rule. So it will be b e to the tb times the moment generating function of at plus e to the tb times m y prime of at times a by the chain rule. So therefore, if we do mw evaluated at 0, this will be b times 1 times ny to the evaluated at the 0 plus e to the 0, which is 1, times ny prime of at, but at will just be 0, and then it will be times a, which it will be b times 1 plus 1 times this, which remember that's the first moment, that's just the expected value of y times a. So you rearrange this is a, the expected value of y plus b, which is exactly what we had before. Well, clearly this method was a lot longer than just to find this result the way we did it before, but moment generating functions are very, very powerful, so this is a good way to check that you understand how to use them. Now, if we want to use this same method to find the variance, okay? So remember that the variance equals to the expected value of w squared minus the expected value of w squared, which we already found it to be here. So you just need to find the second moment, and to find the second moment, well, you have to take the derivative with respect to t of the first derivative, okay? Which in this case it will be the derivative with respect to t of all of this beautiful thing right here. Okay, so again, this is just a calculus exercise where you have to apply the product rule and the chain rule. Just give it a try. This will give you the second moment, and once you find the second moment, just plug it in here, combine it with this one. And I did this problem already with a different method, so you can check that, and the answer has to be just a squared, the variance of y. Or in our case will be, you can say this is the expected value of y squared, the second moment, minus the first moment squared. Again, I did this in the previous lectures, just check that. This is just a different way to get to the same result. All right, and that's it for section 3.9. So we're skipping 3.10 for now. We're gonna go now to 3.11. Now section 3.11 is called Chevy's theorem, and if you have taken any previous statistics classes before, like the undergrad, you see this theorem there, and also something called the empirical rule. The empirical rule is something that we're gonna do a lot in detail in this class, like a lot, in once we get to the continuous distributions. But the empirical rule says the following, which most of you have already seen it, but just refresh your memory. If you have the mean and you move one standard deviation to the right and one standard deviation to the left, you should have as around 68% of the probability or the area. If you move two standard deviations to the right and two standard deviations to the left, then between here and here, you should have around 95% of the probability or the area. And then if you do it 3 times, okay, it will be mu plus 3 sigma and mu minus 3 sigma. You have around 99.7%. And if you keep it going, you don't really get much. You can go 1,000 standard deviations, but you will never get to 100%. Now, in this case, you can see that the distribution is symmetrical, but you have many random variables where the distribution is not symmetrical. So therefore, Chevy's theorem is a more general result than this. The empirical rule is you could think of as a special case of Chevy's theorem. Okay, and Chevy's theorem, this one works regardless of which distribution you have. okay, of the, or you can say regardless of the random variable, which is a big deal, but it also is going to be very restrictive because it has to be in general. Now, what the Chevy theorem says is the following. Let y be a random variable that has a mean and a finite variance. Then for any constant k, so k is going to be, you can think of k as the number of standard deviations, and k that is not an integer, it can be any real number, positive or negative. Okay? Then this tells you the probability regardless of whether you know the distribution or not. Like for example here, it doesn't say that this is binomial, Poisson, or geometric. It just tells you it's a random variable which obviously has to have a mean and a variance, but it doesn't tell you how the probabilities are distributed. So if that's the case, in some sense you could think this is like the best you can do. Now recall from algebra, okay, and I don't mean abstract algebra, I mean from basic algebra, that you have this mu y minus mu is less than k sigma, that this is the same thing as minus k sigma less than y minus mu less than k sigma, or the mu minus k sigma less than y less than mu plus k sigma. Okay, so this is something from elementary algebra, but we're gonna need the result right now. So what this is telling you is the probability the mean will be within this many k standard deviations, or the probability that y will be within these k standard deviations from the mean will be equals to this, where k, like I say, is the number of standard deviations. Notice that k has to be positive, but if k is equals to 1, this is no good. Why? Because it will tell you the probability is equals to 0, which is not true. Okay, so therefore k has to be positive, but technically 1 is not the best choice, so you can pick any other value. If k was equals to 2, doesn't matter what distribution you have. Notice that 1 minus 1 over 2 squared is equals to 0.75. So therefore that means that if you move 2 standard deviations to the right and 2 standard deviations to the left, the probability has to be at least 75%. Notice that the empirical rule has much more than that, so this is more conservative. If you move 3 standard deviations, then it will be 1 over 3 squared, or a over 9, which is around 89%, which again is less than the 3 standard deviations from the empirical rule. Okay? So in essence, you can just plug in any value for k, and you'll get a proportion or probability. The only one that doesn't give you a meaningful thing is 1. You plug in 1, you will get 0, which, remember, the probability of something being 0, that means it's an impossible event, and that may not be the case here. Okay, so now let's do a very specific example, which is just a twist of these values right here. So here it is. So let's say that y is a random variable. Again, we don't know the distribution. We just know that the mean is 10 and the variance is 4, which means that the standard deviation is equals to 2. And it's asking you to find a lower bound, which is what I say. Here the 75% is a lower bound, so it means that if you move 2 standard deviations, you need to have at least 75%. So that's what it means by lower bounds. So you could think these are lower bounds. Now it is important to notice one thing here. if y was a binomial or Poisson or geometric distribution, you should be able to find this precisely just using the density functions or the mass function. Since this distribution is unknown, therefore the best we can do is to find a lower bound using Chevy-Chase theorem. And for that, you need to figure out the value for k. Now, notice from here that the distance between mu and this and mu and this are the same, and they have to be. If that's the case, then you can figure out easily what's the value for k. Remember that mu plus k sigma has to be 15, or you can say mu minus k sigma has to be 5. So you can use either one. In our case, mu is 10, k is what we're trying to find, sigma is 2, this is 15. So that means that k is equals to 5 over 2. Therefore, this is equivalent to saying the probability that the absolute value of y minus 10 is less than or equals to 5/2 times 2, where this will be k. And by Chevy-Chase theorem, this is equals to 1 over k squared. Will be 1 minus 0.16 or 0.84. So that's the probability. Remember that that's a lower bound. It could be higher than that, but this is the smallest that has to be. All right, so let's do one more problem. The US Mint produces dimes with an average diameter of 0.5 inches and a standard deviation of 0.01 inches. Using Chevy-Chase theorem, find a lower bound for the number of coins in a lot of 400 coins that are expected to have a diameter between 0.48 and 0.52. Right, so notice here we have the following. Mu is 0.5 and sigma is 0.01. So here, if we want the probability between 0.48 less than y less than 0.52, notice that here is obvious that the value for k is 2. Why? Because 0.50 plus 1 is standard deviation is 51 plus 1 more is 0.52. So clearly the value is k. So using Chevy-Chase theorem, this should be 1 over 2 squared. So it will be 0.75. So therefore the expected value is going to be 400, because you have 400 coins, times the expected value of each of them, which is 0.75 or 300. So that's how many you should expect to have. And that's it. Now we're going to see this theorem multiple times. We just saw right now for the discrete case, but we will see it also for the continuous case. And again, the good thing is that this theorem works if you have no idea what is the distribution. The bad thing is that only gives you a lower bound, but it's better to have a lower bound than to have nothing, I guess. All right, so that's it for 3.9 and 3.11.